In this fragment, I will show you some exercises from section 6.3. Let me start with exercise 9 on page 166. Here is R is an integral domain. And assume that the principal ideal and P is an element of R. The principal ideal P is prime. Prove that whenever P is a product of two elements, C, D, then C or D is a unit in R. Here is how the proof goes. We have that CD is P, which is certainly an element of the ideal. Integral domain contains 1, so this ideal has an identity, so this ideal contains P, because now the ideal is prime, by definition, a product of two elements belongs to the prime ideal, implies one of them, therefore at least one of them must belong to the ideal. I want to prove that one of them is unit. Unit is in an ideal if and only if, in an integral domain, if and only if the ideal is the whole domain. So I will, that one which is unit definitely is not in the ideal. I will put it this way: if C is in the ideal, then D is a unit. That is what I want to prove. That suffices because integral domain is commutative, so either way, who is C, who is D, does not matter. If D is an ideal, then C is a unit. So that is the statement I want to prove. Thus, I assume that C is an ideal, sits inside ideal, and the ideal is principal. So C belongs to the principal ideals means that C is a multiple of P, PR, with some element R in the ring R. We thus have P is equal to CD, and we can rewrite P equals CD as P equals CD as P equals PRD. Now we can take PRD to the other side, add negative PRD to both parts of the equation. P minus PRD is 0 in the ring R, and we can factor P out. P identity minus RD is 0. A product is 0 in an integral domain, since R is an integral domain. We have that P is 0 or 1 minus R. D is 0. I forgot they told us in the very beginning that P is not 0. Well, otherwise, otherwise this ideal contains nothing but 0. Zero, of course, may be a prime ideal, but a factorization of 0 in an integral domain will give us nothing. One of them is 0, and another one maybe not a unit, but anything you want. So this is absolutely necessary, which I just forgot to write here. So since I wrote this, since P is not 0, we conclude as P is not 0 was given, or otherwise the question was incorrect, we conclude that this is 0 means 1 in the integral domain, or other way, let me write it other way around. We conclude that RD is equal to 1, which by definition means that D is a unit. it has an inverse. Integral domain is commutative, so we don't need to care about right and left. It is just a unit. Immediately, RD is equal to dr is 1, so d has an inverse. That is exactly what we wanted to prove. That's all. The exercise is done. Let me show you another not so difficult problem from this set of exercises, and that's going to be 20 on page 167. They want us to find an ideal in Z cross Z, which is prime but not maximal. The solution for the solution let me first recall what Z cross Z is. Z cross Z, by definition of Cartesian product of rings, is the set of ordered pairs AB, A and B, both integers. And the operations here, this is a ring, operations are defined by component-wise addition and multiplication. A plus C, B plus D, and AB times CD is AC BD. These operations make the set Z cross Z a commutative ring with identity. The identity is going to be 1, 1. You easily check that 1, 1 is neutral element for multiplication. And this ring is not an integral domain. We have that 1, 0, for example, times 0, 1, according to this rule, is 0, 0. That is 1 in Z cross Z, and this is, of course, 0 in Z cross Z. So you easily check that these are these elements in the ring. This was just what we are to recall what we are speaking about. And now back to the problem. So we want to find an ideal. I will find this ideal as the kernel of a homomorphism. So consider the map from Z cross Z to Z, which takes a pair AB and maps it to A0, or just to A. Both of them are integers, we just take the first component. It is easy to check. I believe you can do that, especially when I have recalled what the structure of Z plus Z is, so easy to check that this map is a ring homomorphism, and the map is of course surjective. Any integer appears in the image because any integer can stay as the first component. So the map, this map, is a surjective homomorphism. Thus, we can look at the kernel of this homomorphism. The kernel and it is also very easy to see which elements map to 0. As soon as A is 0, this is going to be 0 independently on B. So the kernel, call it K, is the set 0B, B in Z, the kernel. So this is the kernel, and you don't really need to check that K is an ideal. This is an ideal because it is the kernel of a ring homomorphism by theorem 6.10. That the map is ring homomorphism, you check immediately from this definition of operations on Z cross Z. You check that sum maps to sum of A's on the first component, product maps to product on the first component, and you are done. You don't need to really apply criterion. That it is easy. In fact, that this is proving that this is an ideal. Any kernel of a homomorphism is an ideal. Now, we have surjective homomorphism. We have determined the kernel, and theorem, the first isomorphism theorem, allows us to conclude that this is theorem 6:13 in the book allows us to conclude that z cross z factored over the kernel is isomorphic to the image z. Now, what can we tell about this image z? Z, this ring is, this is the ring of integers. This is our first example of an integral domain but not a field. Not every element is a unit, of course. There are very few units here. Thus, from here, from the fact that this is an integral domain, we conclude that the ideal K is prime by theorem 6:14, but not maximal. By theorem 6:15. So every field is an integral domain, so every maximal ideal is prime, but not every integral domain is a field. Z is an example, so not every prime ideal is maximal. So K is immediately an example of an ideal which is prime but not maximal. That is a solution for this question. We did it. And let me do yet another exercise which in a sense is very similar, uses same ideas, but there is a subtlety which I want to address. This is exercise 11 on page 166. Show that their principal ideal generated by x minus 1 in the ring of polynomials with integer coefficients is prime but not maximal. As in the previous problem, that will follow from z over z of x factored over this ideal is isomorphic to z. Again, same argument, exactly same argument applies, because same z, which is an integral domain, and is not a field. By the way, the isomorphism is parallel to factored, same ring factored over this ideal x. Principal ideal generated by x is also isomorphic to z. And that is example 7 on page 164 in the book. So the kind of difference between this principal ideal and this principal ideal is really slim. Still, we're going to prove this isomorphism. After that, everything is clear. Now, in order to prove this isomorphism, we, of course, so we're left to prove this isomorphism. And I will not again comment why that implies that the ideal is prime but not maximum. We consider the map from polynomials with integral coefficients to integers when a polynomial is taken to its value at 1. This map is a ring homomorphism. We need to prove that sum of polynomials maps to sum of values, and product of polynomials maps to product of their values at 1. We know that about polynomials with coefficients in a field. Unfortunately, z is not a field. But where I don't want to check it again, I will say that that is because the map, the corresponding map Q of x for fields, the situation is much easier. And we already know that this map, taking value of a polynomial, Q is a field. And we know we proved in previous chapter that the map from polynomials with coefficients in a field to the field taking any value is a ring homomorphism. This is a homomorphism, so this also is, because we want sum maps to sum of values. Every polynomial with coefficients in z can be considered as a polynomial with coefficients in Q. After all, every integer is a rational number. And after that, some still we stay in this ring, but we are also inside this bigger ring, and the sum maps to sum of values. Same with the product. So we don't need to really check for polynomials with coefficients in a ring. Here we may pass to an easier situation where we did everything for the field. And this homomorphism is surjective. That I will write here, the map is surjective. We cannot derive it from this statement, but from the statement about polynomials with coefficients in the field and rational numbers, but that is obvious. We can make up a polynomial easily with any value at 1. Namely, constant polynomials will do the job. Their values at 1 are these constants themselves, so the map is surjective. So, constants, polynomials, already do the job. We have a surjective homomorphism. We can consider its kernel, of course. And we expect that the kernel is that ideal which we want to consider. So we want it the kernel as the ideal generated by the polynomial x minus 1. Indeed, that would suffice. The surjective homomorphism with this kernel will give you, by the first isomorphism theorem, this isomorphism, as exactly as in the previous problem. So that would suffices by the first isomorphism. Theorem. Let us look at the kernel. So that is all we want, that the kernel is the principal ideal generated by x minus 1. And in fact, the kernel is, well, what is the kernel of this map? This is a map which takes polynomial to its value at 1. So the kernel is the set of all polynomials such that the value at 1 is 0. These polynomials map to 0. Is this kernel equal to that? Clearly, or the kernel, or let me denote this kernel as K. Clearly, kernel contains this principal ideal. Now, indeed, if f is equal to q to x minus 1 times q, with a polynomial q in z of x, whatever it is, then f of 1 is 0. This is very clear. But the subtlety is the opposite inclusion. So we need that kernel sits inside that. Meaning, what does it mean? That, in other words, we want to prove that f of 1 is 0, f belongs to kernel. Kernel is all polynomials with this satisfying this condition, implies that f is equal to x minus 1 times q with some q in our ring. Now we can apply remainder theorem that is theorem 415 in the book, tells us that this theorem is not about polynomials with coefficients in a ring. The theorem is about polynomials with coefficients in a field, and that is the subtlety. Otherwise, everything is easy. Remember, the theorem tells us that we think about polynomial. I want to apply the theorem. I will think about the polynomial as a polynomial with rational coefficients. Now, every integer is a rational number. Then I can apply remainder theorem, which tells us that it's kind of combination of a little addition to Euclid's lemma. It tells us that f is equal to x minus 1 times q plus f of 1, and f of 1 is 0. That is what the remainder theorem tells us, that we can divide polynomial f, whatever it is, by x minus 1, and the remainder is going to be the value at 1. The value at 1 is 0 for the polynomials we consider. And since f of 1 is 0, we have f as x minus 1 times q. But with q, a polynomial with rational coefficients. And that is what I wanted to address here, why I at all wanted to discuss this problem with you. We are almost there, but we need f of 1 equals 0, and we need this one. That is all we need. What remainder theorem tells us is this one, and the difference is here. Remainder theorem guarantees, as soon as f of 1 is 0, the existence of polynomial with rational coefficients. Everything was overfilled. Of course, I can consider any polynomial with integer coefficients as a polynomial with rational coefficients. But I cannot go backwards. Not every polynomial with rational coefficients is a polynomial with integral coefficients. So now all we need to prove is that actually, so we want to prove that f is still a polynomial with integer coefficients, then so is q. Then we are done. Then we are here, and that is what all we needed for the opposite inclusion. We are done. So the last effort, and that is the subtlety in this problem. Why at all we dealt with that? We want z, not q. All phenomenon, I will remark about that a little bit later after we finish the problem. All phenomena we consider, ideals which are prime but not maximal, happens in this ring, does not happen here. So we do need consider for this question polynomials with coefficients in z. That's indeed absolutely necessary for these examples of ideals which are prime but not maximal. So let us do the proof. Now we have that f has all integral coefficients. Okay, let q, this polynomial, be some polynomial a naught plus plus a n x to the n. And let us write that, so let us expand x minus 1 times q in fact has integral, not rational coefficients. So a's are all rationals, but we know that after multiplication, the coefficients are integral. So let us multiply x minus 1 by q. That is, okay, negative a naught. I multiply x minus 1 by this polynomial. The constant term is going to be negative a naught. The coefficient of x is going to be a what is going to be the coefficient of x? Negative a1x plus a naught x. So plus a naught minus a1 x plus x squared a1x times x, a1x squared minus a2 negative 1 a2x squared, x squared. And so further until the last terms. So let us see what the last terms are. So it is going to be an, it is going to be an negative, it is going to be an minus 1 minus an x to the n, and the very last term, this is penultimate term, and the very last term is going to be an x to the n. This is the product which we know belongs to the polynomial ring with integral coefficients. What does it mean? This means that negative a naught is an integer, so a naught is an integer. This also means that this one, a naught minus a1, is an integer. But we already know that a naught is an integer. Therefore, a1 must be also an integer. Now, a1 minus a2 is an integer. But we already know that a1 is an integer. And that implies a2 is an integer. And now it is clear how do we proceed until the very end, when we find that a n minus 1 minus a n is an integer, implies no, we don't need that, because the very last is going to be not this one. The very last is a n minus 2 minus a n is an integer, minus n minus 1 is an integer, implies a n minus 1 is an integer. A n is an integer for free. Lastly, a n is also an integer. without any assumption when no a naught and a n are integers immediately. That's all. That tells us that, in fact, Q is in Z of x, not merely in Q of x. And that is the end of story. That was the last statement. We wanted to prove that our Q has integral not merely or not merely that is what we want to prove, not merely rational coefficients. So the problem is solved this way. We found an example of another example of an ideal which is prime but not maximal. We found it very similarly to the previous problem. This example is a little bit better because in the previous problem, that is a kind of cheating. This ring has 0 divisors. This is not an integral domain. So the question was, is it important or not so important? We found an ideal which is prime but not maximal. We found that in a ring which is not an integral domain. Now we have an integral domain. This ring is an integral domain where we have an ideal, again, prime but not maximal. So it is, in a sense, a better example of an ideal which is prime but not maximal. What we used our knowledge about coefficients with rational coefficients. In fact, that is how one works with this kind of rings, with coefficients in Z or integral domains more generally. One passes to the field and uses the knowledge about polynomials with coefficients in the field, which is way simpler. After that, we can go back. And sometimes, you see, going back was not a completely trivial thing. So we knew already that we found Q with rational coefficients, but we needed a little bit of very explicit, in this case, calculation to find that everything still works for polynomials with integral instead of rational coefficients. Okay, that is what I wanted to tell you. So be careful, these polynomials in this ring, they really have pretty good properties parallel to polynomials in this ring, but still not, it is tricky. And in particular in this ring, we have polynomials, we have ideals which are prime yet not maximal. There is no such ideals in this ring. In this ring, every ideal is every prime ideal is maximal. We will come closer to distinctions to the arithmetic in these rings a little bit later in chapter 10 of the book. And that, I believe, is all for the problem session for chapter 6. Thank you for listening.